Hello and welcome to RF Design Tutorials. This is Tutorial 18 on Practical Power Amplifier Design. This is part 3 of the tutorial series. The objective of this 3-part tutorial series was to take you through a complete design process for a practical power amplifier, starting from a simple device, moving over to complete circuit and layout design, performing the validation of the virtual PCB assembly, and finally do the modulation analysis and look at the techniques to linearize our power amplifier to achieve the desired modulation quality. Now, before we start with this tutorial, please subscribe to my channel. Once you subscribe, don't forget to hit the bell icon to enable all the notifications. And after you watch the video, give it a thumbs up and share it with your friends and colleagues who may be interested in watching similar tutorial. All right, so just to recollect, in part 1, we discussed about getting started with PA design. We look at DCIV simulations, stability analysis, a bunch of load pull simulations, and finally figuring out what should be the right source and load impedance for our device. In part 2 of the tutorial, we talked about how to perform matching network design and do a layout design for our complete PA and perform the two-tone analysis as well as the swept compression analysis. And finally, we did layout an EM co-simulation and make sure that our PA has the right performance as the specification which we decided to design it for. Now in this current tutorial, we will look at ways and techniques to perform modulated signal analysis because no matter which standard you might be building the PA, it's unlikely that you are building PA for a CW operation. May it be a 5G, Wi-Fi or radar application, every standard will have some kind of modulated signal over which your PA has to be operated on. So in the first part of the tutorial, we will look at different techniques to do modulation analysis. And after we are able to look at the modulation characteristics, we will talk about techniques which can help you enhance the linearity of your PAs as well as obtain the high level of power and efficiency at the same time. So pretty interesting topic to be covered in this tutorial. So hope you will stay till the end and watch and learn all the techniques which you can use when you are designing your own power amplifier circuits. Now, before we start with this video, make sure you have watched tutorial 16 and 17 already because this video is in continuation to the previous two tutorials as we just discussed about. Now, the first question you need to ask yourself, well, why do we use modulated signal? Why can't we just perform the characterization of my amplifier like I always do using one tone and two tone? The situation today is today's standard cannot be approximated by a couple of signs because all the specs are EVM based and then you don't want to do an over designing because meeting the specification itself is quite a challenge. Now here I posted two snapshots of the results which is in the 5G document. Now, if you look at one of the requirements is to make sure your PAs or transmitters have the required matrix to be met for EVM, which is error vector magnitude. Depending on different level of modulation you use in the signal, you have various EVM specs to comply for. Also, in terms of out of band distortion, you have ACLR limits, and depending upon which technique you are using, there are different specification to find out the ACLR for one bandwidth offset, two bandwidth offset, and so on. So these specifications are very hard to come up with if you're using one tone or two tone kind of methods because that more often than not will lead to over designing because you are maintaining a certain cushion for yourself in terms of having extra margin in designing. Well, we don't need to do that. So a good technique if you're using ADS is to use circuit envelope simulator, which is a combination of frequency domain and time domain simulation, which is what precisely you need to perform modulated analysis. So we will learn all the techniques we have available for designers to use. Now, what are the options inside ADS to perform modulated signal analysis? Well, approach number one is to use VTB, or what we call as virtual test bench, and I will give more details about that, or a regular circuit envelope based analysis. The, the advantage of this is there is no simplification or circuit model extraction needed. However, it suffers from a large simulation time because you're simulating lots and lots of symbols to cover the desired frame or the time length which you're going to simulate. So it's difficult to use it as a design exploration tool, and mostly designers use it as a final verification step like we are trying to do now. Now, approach number two, which is pretty much can be used as a design tool during your design phase of the PA, using compact test signals, or in short, what we call as CTS. And then to perform EVM measurement, we do have a function called distortion EVM. So the advantage of doing that is your simulation will run much faster, and it can be really used as a design tool so that you can characterize your PAs over swept power conditions, bias levels, and so on. The disadvantage or thing to be watch out for is a partial waveform based validation. So user needs to be sensitive about the length segment which he uses in the simulation. But again, it's not a rocket science, it's a simple thing which you need to take care of. Now in approach number three, we have a technique called fast circuit envelope, or FCE. Again, the advantage here is using this technique, you can perform faster simulation. You can use that technique as your design tool so that you can really use these techniques when you are designing your PAs and sweeping various parameters. And as a side effect, you also end up generating a behavioral model, which we call as FCE model, which can be shared with your system designers so that they can perform a system level verification using your IP, but you without disclosing your IP to them. The disadvantage on this side, and where you need to be careful, is you will need a behavioral model extraction to use this approach. We will now look at each of these approaches in a little more detail, and all of them have their own place during depending upon where you are in terms of in your design phase or product development phase. So you will in reality end up using all three of them at different phases of your design work. So let's go and talk first about VTB, which I said is virtual test bench. Now VTB basically is a way where you can actually bring in keysight grade measurement IP into your simulation world, and it just looks like this black box. So the signal which comes out of VTB is almost equal to what comes out of a keysight hardware in your real world when you're testing your DOT. And then the output of your circuit is fed to the receive branch or the input of this VTB, which will do all the number crunching and perform modulated analysis, like how a traditional spectrum analyzer or vector analyzer will do for you. Now, in terms of VTBs, you have large selections to choose from, and there are plenty of standard VTBs available for you to plug in and configure the waveform the way you want. Now, in case you need custom VTBs for your own unique specification, if you have a copy of System View, which contains plenty of wireless libraries, you can virtually create your own VTBs with a custom specification or a complete customized waveform as you need. But that's an optional step in case you are working on something very customized. Now let's look at how do we run VTB based simulation in ADS. Now before we reach there, just for make sure we are sync back to the topic which we already covered in the previous video. At previous video, we stopped at this point where we performed a complete EM circuit co-simulation of our PA, and once we run the simulation, we did observe the power swept characteristics of this virtual PCB, and we saw that around 3 dB operating point where we wanted to put our transistor, we were able to get 40 dBm output power and pretty high efficiency of 62%, which is power added efficiency. So this is where we left in the last video. So now let's go ahead and talk about modulation analysis. Now, in terms of using VTB, in ADS, you can open up any schematic. And VTB, just one good point to note here, the VTBs, the virtual test bench, is an add-on installation. That means you can go to Keysight, ADS download location. That's where you download ADS from. And there is a small add-on utility for you to download and install in ADS. And you should have VTB license in order to run some of these benches. Once you configure, the VTB will appear under simulation category. And here, if you look at simulation VTB, you will find few components. Now, depending upon what signal type you need for VTB, if you click on this basic icon, you can see these VTBs are generated by system view using a specific version. But as new system view version comes out, you will have newer VTBs to use in case you need a newer standard or newer verification. Now here you have different VTB categories. So you have 5G, Bluetooth, DPD, as well as envelope tracking, LTE, LTE Advanced, NB-IoT, WLAN. So there are plenty of standards to choose from. For example, if we go ahead and select 5G VTB, then you can go ahead and select what kind of verification or virtual test bench you need to do. In our case, we have used the downlink transmitter because remember, we are creating an amplifier which will be typically used in a base station kind of application. So here I have used a downlink transmitter analysis. And once you click OK, you will have a black box like this, which you already see on my schematic. It has a source output and it has a sink input. So the source output waveform will be fed to your PA, and you have a PA inside. And if I push inside is basically the same virtual PCB assembly, which we are going to feed the 5G waveform, and the output of that amplifier will be sent back to this VTB to perform the analysis. Now, how do we set up the characteristics of this VTB? If I double click here, you can see you have frequency carrier in, carrier out. So what this tells you that even if you are working on some frequency translator device, such as your transmitters or mixers, you can also have different input and output frequencies. But in my case, it's a simple power amplifier. So both of them are same. And then you set up your power. If you want to introduce any imperfections to your signal, you can do so as well. Then you can decide the bandwidth. So remember, we are dealing with 5G. So you have these kind of bandwidths available. So the way I have set up my verification here is for 100 megahertz bandwidth. And here is the oversampling ratio. I'm oversampling with ratio 4 to allow me to have sufficient bandwidth at lower and upper sideband so that I can perform an ACLR calculation accurately. Now, again, you can go ahead and set up the parameters like you need for the unique 5G signal you're trying to create. Now, if you don't need to go through that, all 5G standards have various test models described already. So if you go ahead and pick any of the specific test models as provided in the reference standard document, the bench here will automatically set the required parameters which you need to comply your DUT for against a certain test model. So if you don't want to use test model, you can always set this use test model to no, and then you can go ahead and define your own SSB, your PDSCH, your modulation, depending upon whether you need QPSK, 16 QAM, 64 QAM, or 256 QAM. So all these parameters you can set. But if you already declared a specific test model to be used, then you don't need to worry about those parameters because the source will configure itself the way you are looking for. Now, as simple as that. So once you have VTB, you can also in the VTB, you can look at the summary. You can query the VTB description, and that gives you the information for what purpose or with what specifications have you set the VTB. And also, in order to help you perform simulation, you can have an envelope controller and you can insert envelope controller so that envelope controller with the right settings get placed on your schematic. Now, when we query the VTB carrier frequency, you can see what all things it is going to measure, what standard is it referring to, what date that standard was released, and so on. So all those information is right upfront for the user to check. Now, once you go ahead and run the simulation, this takes quite a bit of time. So I'm not going to run the simulation for this demo. You will have a on an automatic data display come up with bunch of data available. So what I have done, I have removed some of the data so that I can only focus the key things I'm looking for in this particular video. So one of the measurements will be EVM, and here you can see EVM in percentage. So at my operating condition, the EVM produced at the output of my amplifier is around 6%, and ACPR of lower and upper, which is one bandwidth offset, is around 33 dBm. And you can see slight disbalance between lower and upper ACPR that tells you that your PA has a bit of memory problem. So we do have a memory effect coming in to our PA, but they are not drastically different. So that means the memory effect is not that dominant. But we will talk about some of those as we reach the DPD stage. Also here you can see the characteristics of the output power, which is above 40 dBm, which we are looking at our operating condition. And also you can look at CCDF. Now CCDF is simply the measure on x-axis. You have a power in dB relative to average power. On y-axis you have the percentage. And if you look at 1%, if you place a marker here, you can see how much is your peak power above the average power for 1% of the time. And in this case, you can see it's close to 7.3 dB. So that's a kind of dynamic range you will be dealing 1% of the time and so on. So CCDF gives you a pretty important matrix to understand how much peaks are you going to face for how much percentage of time. So this modulated analysis, our PA looks pretty good, not bad, right? And here you can see spectrum, the blue, which is plotted on the right y-axis is the input spectrum, and the red is output of your amplifier. And here you can notice the distortion or the sideband, which is due to the PA nonlinearities, and that's what we refer as out of band distortion. And EVM is the measure of in-band distortion. Now again, if you go back and try to find out where can I get all this specification for how much EVM I should need, what ACLR I should need, and how much setting or what kind of settings do I need to do here in terms of numerology, resource block, and some of those in case you decide to set it for yourself. Well, you can go to the etsi.org website, and here I have the base station channel bandwidth configuration, and here are different bandwidths and the subcarrier spacing, or what you call as CS, and the number of resource block which you need to have in your waveform. So all that detail is here. Also, if you want to check how much is the EVM specification, if you go to page 44, here you can see depending on different modulation schemes, what kind of EVM you have to match. And further down, if you scroll, it will also tell you about ACLR. And here is the same snapshot, which I just showed you earlier. Depending upon what bandwidth offset you are looking at, you can look at ACLR limit, which your PA or base station has to comply. And whenever we say base station limits, usually PA is our output most device. That becomes a PA specification. So at output of a PA, you should have these ACLR and that EVM specifications to be met. All right. So hopefully there's no confusion here. All right, now let's go back to our presentation. We just talked about how simple it is to use VTB, configure the signal which you want, whether it is 5G, Wi-Fi, radar, and those. Now let's go ahead and talk about the second approach. VTB is pretty good, but as we talked about, it's a time-consuming simulation. So that means each simulation you run, depending upon the oversampling ratio to cover the desired bandwidth. And if you are going to cover one frame or half frame of 5G waveform, imagine it could be hundreds and thousands of samples which you need to run for simulation. So there is always a compromise between how much time you have available in order to do analysis. And if each simulation takes 1 hour, which is good for as a final verification step, but if you really want to see EVM or ACPR, or if you want to optimize your PA for a certain EVM, you can't really use virtual test bench as your design tool. So here is the alternate, which is an excellent alternate. And this is a new concept which Keysight came up, and it was presented in one of the IMS workshop by one of our measurement scientists. And here's the concept goes. If you look at a traditional EVM, how we analyze our waveform, you need a full frame or a half frame kind of data. And you need things like preamble, pilot data, because the way you are computing EVM is based on each symbol. However, the new concept talks about compact waveform, where out of this entire waveform, let's say one frame of data, if we can find a slice of that waveform, which will represent the same frequency signature as well as a statistical distribution in terms of CCDF to make sure you capture the right PAPR, then we don't need necessarily this entire waveform. We could do our validation by this compact test signal or a small slice of the waveform. So how do we find that the right duration for that chunk which we need to use for simulation? Well, here's a simple formula. If you know the inter-carrier spacing, or what we call as TF, which is tone spacing, if we take a simple reciprocal of that, you get a good estimation of how much minimum time you need. For example, here, if your intertone spacing is 100 kilohertz and you take a reciprocal of that, you will end up getting 10 microsecond. One frame of the 5G data is 10 millisecond. So instead of running 10 millisecond long simulation with a very high sampling rate, I could simply run the analysis for the simple 10 microsecond. You can tell yourself the simulation will run a lot faster, and it will allow you to do things like optimization on your design. Similarly, if you take a look at your 5G signal, if you use 10 kilohertz of carrier spacing or intercarrier spacing, you will need 100 microsecond of time. Now, when we take this chunk, we also need to look at the comparison of CCDF, because smaller chunk you take, bigger could be the difference in between the ideal signal or the real signal CCDF versus what you are using, and you might underestimate the distortion. So be little careful about that, but no matter what you do, your simulation will still run very fast. Now, what happens behind the scene? So once we take this small signal, obviously we cannot compute EVM using the traditional way, where we are doing symbol-based EVM calculation. And that's where this distortion EVM comes in very handy. Now, the technique behind this distortion EVM is like this. When you look at any output signal, let's say Y of F, you see in-band distortion, and you also see out-of-band distortion, which you commonly refer as ACPR or ACLR. Now, if you decompose this spectrum in two parts, one which is the linear part of this spectrum, which is essentially the in-band kind of signal, and you decompose it to linear part, and then the second component becomes your distortion part. So when you put it together, you basically get this overall modulated spectrum, which is distorted. Now, using this distortion part, we do EVM computation directly in frequency domain. So I really don't need to have the complete frame of the signal or half of the frame of the signal to do my computation. And the logic behind it, well, as per Parseval's theorem, EVM computed from time domain or frequency domain are mathematically equivalent. So it doesn't matter whether you do EVM calculation in frequency domain method, like what is employed in distortion EVM inside ADS, or when you do a full symbol based EVM, which is traditionally how you do it using signal processing. Now here is a comparison and a demo amplifier, and I will also show you comparison on our Cree device, which we are building our amplifier on. Now for a 180 nanometer CMOS preamp, here is a comparison. The blue curve is EVM calculated in frequency domain using distortion EVM. The red is data flow EVM, what we are doing in system view, which is our mixed signal system simulator. And if you compare the results between distortion EVM, which is a lot faster because we are only operating on a small chunk of data versus a full frame kind of signal, you can see a pretty close correlation with difference of only about 0.3 percent, which is excellent. If I have to do my simulation in few seconds versus 1 hour or a couple of hours, so it's a pretty good and proven technique. It's a new technique in the market, so a lot of designers are still doing their own validation before they employ. And again, as a recommendation, we always recommend designers to run bunch of validation themselves to find out what is the sweet spot where you can really use this function and gain the speed advantage. Now also in the newer ADS versions, we also added a capability to do EVM versus time while using distortion EVM, because many a times the regular EVM value which you see is a typical RMS. So if you're measuring or you're performing simulation of one frame, half frame, it's the RMS EVM for the complete measurement chunk which you have. However, in certain cases, looking at EVM versus time can give you a lot of advantage, especially think about if you're doing things like envelope tracking. So you can really see EVM as it changes versus time, and you can define the interval. So this is the function which you can simply put it on your schematic or data display. You can define your input node name, output node name, and the time intervals or time chunks on which you want to do EVM. At the end of simulation, you would be able to see how EVM is varying over time or different time chunks. And eventually, the EVM value which it reports will be an RMS for this entire chunk. So you get best of both worlds here. So that's the second concept. So let me show you how simple it is to set up a compact test signal based simulation in ADS, and then how to use distortion EVM as the function to do the verification. So here in my second bench, I have you. Right. So in order to set up simulation here, you just need to place an envelope simulation controller, like you placed harmonic balancer or S parameter and so on. So here is your circuit envelope. Once you place this envelope, you can define the characteristics such as your carrier frequency, time step at which you would like to sample the waveform, how long would you like to sample, and so on. So currently I have a waveform which is quite long, and I can define the t-stop to be 0.1 millisecond, and I can run or 1 millisecond depending upon how long is this waveform. And that technique would run a regular envelope simulation, no change, and you would be able to look at output spectrum, use distortion EVM to compute the EVM. Well, the compact test signal, here is a check mark. So once you enable compact test signal, you can define the length which you want to simulate. So what happens, when I run this simulation, remember, if I go back to slide, we talk about finding the right slice of the waveform from this entire frame. And we already decided, like in my case, I'm going to use 10 microsecond of the signal. So the question is, where is that 10 microsecond good signal located in the entire frame structure? Well, that's the job which algorithm inside ADS is going to do for you once you declare how much time segment you need. And that information as a first step, ADS will run, and it will report the CDF error function here. So you can see it is saying compact test signal is generated with the CDF error, which is your CCDF error of 0.0065, which is pretty good correlation between the real signal CCDF curve versus what we picked up as a 10 microsecond time chunk to be analyzed. Now, in terms of doing the EVM measurement here, you can either set these equations in the schematic or data display. The advantage of putting this EVM calculation in schematic is now you can actually set this as an optimizable goal, and you can optimize your PA design to achieve EVM below a certain limit you are looking at. So for distortion EVM, the simple function to use is distortion underscore EVM bracket, and it needs two arguments. One, what is your input node, and two, what is your output node, so that it can compare the input and output waveforms, do segregation between linear part and nonlinear part, and then using the nonlinear part, it can do your EVM computation. So in and out here is my node labels at the input and output of this PA. And that's what my distortion EVM is going to use. Now, if you look at the status of window here, so the analysis is running behind the scene and it's doing its calculation, but it's going to finish its calculation pretty soon. And let's continue talking about, the other technique in the meantime while it is running the simulation. Now, if you look at another technique of doing, modulated signal analysis in ADS, is called FCE modeling or fast circuit envelope modeling. So what happens behind the scene when you have an input signal and you're trying to analyze an output signal? What's the path to do this analysis? Well, traditionally, what I just talked about in VTB, or if you run a regular circuit envelope, you have hundreds and thousands of time samples because you're sampling at a specific rate, and you have a, let's say, 10 millisecond long signal to be sampled. At every time sample, you are going to run a harmonic balance kind of simulation. So it's like equivalent of running 200,000 or 300,000 harmonic balance simulation to capture this time varying amplitude and the right, distorted spectrum. It's a very accurate technique, but it's slow. So possibly it's kind of impractical to explore the design space for, if you have a lot of variables to sweep, such as input power, or bias voltage, and temperature, and so on. So in alternate technique, we employ a fast envelope technique whereby we first extract the behavioral or a macro model of our circuit. Once we have the macro model, then we go ahead and employ the nonlinear simulation on that. So it runs a lot faster because you already extracted a macro model, so that you don't need to solve voltage and current in each node of your circuit and look for KCL and KVL kind of convergence. You can directly run those nonlinear analysis on the behavioral model you extracted. So this simulation runs a lot faster and results in a very accurate results in the output as long as you do the right modeling. So let's talk about what is right modeling. So when you extract or when you set the simulator inside ADS to use FCE technique, there are three levels on which you can extract the behavioral model. Level one is the fastest, but it's a memory-less model. That means if your PA has a memory problem, and typically that happens once you go into medium to wider band kind of application, this model is not recommended. But if you're working with 10 megahertz, 20 megahertz kind of signal, that's pretty good enough actually in most of cases. So behind the scene, ADS will run harmonic balance with input power sweep to extract AM to AM, AM to PM curves, and that will build your level one model. In level 3 model, along with doing harmonic balance for the power sweep, we also sweep the fundamental frequency a separation between two tones to capture the nonlinear distortion and memory problems. And it also does a small signal mixer mode for power and frequency spacing sweeps. So that results in a good model for both narrowband as well as wideband applications. If you are doing PAs, receivers, transmitters, when you apply a wideband, such as 50 megahertz, 100 megahertz kind of bandwidth. In level 5, which is the most advanced model, but much slower. So here, this is the fastest. This will be little slower, and this will be the slowest, but with the best possible accuracy. When I say accuracy, doesn't mean it will be needed for every application, but if you have a highly nonlinear wideband application dealing with things like detectors, PAs, transmitter, receivers, then you can use this level 5 approach. So we will do harmonic balance with P in sweep, and along with that, we will also do pulse-based simulation with power sweep. So that will give you the required accuracy which you are looking for while dealing with those kind of simulations. Now, if you compare the time as well as accuracy of this fast envelope, you can see the traditional envelope takes 1 hour, but with fast envelope, you can do the same thing in 5 minutes, and the results are pretty consistent between those. And again, there are 3-watt gas PA for LTE signal. This 2-watt CMOS envelope tracking power amplifiers for LTE. And here you can see the speed ups are just tremendous, so that you can really use this fast envelope technology as your design tool instead of a verification tool. So pretty accurate. All right, so that was about fast envelope. So now let's take a look at an example of how do we set fast envelope inside ADS and how we can get benefited out of fast envelope. Well, setting up fast envelope was very similar to the same case like in this test bench here. So in this test bench, when we had this modulated signal going in, and it's a good point actually to talk about how can I get modulated waveform in my ADS for doing circuit simulation. Well, here, let me minimize this trace for a time being. So here you can see I'm using P1 tone source, which is a regular one tone which we use for harmonic balance. But the same one tone source also has this new parameter in ADS called mod, which is modulation function. So using this function, I can put any waveform in a text file or a CSV file in variety of formats, and the same signal source which we usually use for one tone injection, I can actually use it for modulated file read. And the documentation here explains you the format in which it is expecting the data. And here in the P1 tone documentation, if you refer to mod file, it explains the format. And the file is very simple. You can have data in variety of format. You can have time as first column, and the second column is actually your data. And that data could be time and real, or real or imaginary, or you could have time, real, imaginary, magnitude, angle. So it's very flexible. So no matter which tool you are using to generate your baseband waveform, it could be MATLAB, it could be obtained from an instrument which you are generating a vector signal generator, and you can save that output waveform of that vector signal generator in any of these formats, and then directly use that file here in ADS for simulation. Now, while we were talking about this, so our analysis for the compact test signal finished, and here you can see the EVM computed. The RMS EVM is around 6.3%. And if you recall, our VTB computed it to be around 5.9%, which is this result looks pretty good. And here you can see the blue curve is the linear part of your spectrum. The red curve is a nonlinear distortion. And here is the overall spectrum at the output of the PA. And using this EVM versus time function, I'm able to decompose the complete EVM calculation of 10 microsecond, which you see here as 6.3%, into 2 microsecond intervals. And here I can see how EVM is varying between different time chunk. Remember, you're dealing with time varying envelope, and this actually tells you in what slots you have how much EVM. And you can plot that as a table as well, right? So sounds good. Now, the last thing, how do we set up the simulation for fast circuit envelope? Well, inside envelope controller, you can enable fast envelope and you can choose level 1, level 3 or level 5 model. So let me just give you a quick example of level 1. If I switch it to level 1 and we go ahead and run simulation for the desired time, you can see how quickly it ran the simulation. And now you have the results in almost like 1 second. And again, if you compare, it's not very far. The actual VTB was giving me 5.9% EVM, and this technique is ballpark 5.5%. But instead of 1 hour or 20-30 minutes long simulation, I could do that in 1 minute. So again, as I said, VTB is the gold standard, but it can be used as in a final few stages of your design. Fast circuit envelope and distortion EVM are the techniques which you can use in your design phase. So let's switch to level 3 model. And while doing that simulation, let's look at what level 3 model takes. Now you can see here it is running the behavioral modeling behind the scene. And because level 3, it took a little more time. But of course, if you see now, it's around 5.8% EVM, which is a lot closer to what a full frame VTB was predicting. So level 3, because I'm dealing with 100 megahertz of bandwidth, obviously is a better choice to get my results. And similarly, if you want, you can turn on level 5 and look at how much accuracy gets improved if you really run level 5. Now level 5 will run a lot more characterization behind the scene. So as we discuss in this slide, it will be typically the slowest, because first it ran the harmonic balance based extraction, and now it is running the envelope extraction. It is doing the pulsed sweep on your amplifier circuit, and eventually it will come up with a model. So this will be much slower technique. So I'm going to go ahead and stop it here, but once you have ADS license, you have your own PA, go ahead and run all these comparisons yourself and see how they figure out. All right, so these were 3 ways of doing modulated analysis of your PAs inside ADS. Now let's talk about DPD, which is digital pre-distortion. So now let's quickly look at what's the problem statement. Well, we know to get a higher output power, you need to drive PA into, drive it with a higher input power, and that causes high distortion level. But at the same point, you also get a good DC to RF efficiency or power rated efficiency. Now at that operating point, you can see here at the TDB compression point, I'm able to get a higher power as well as I'm able to get pretty high frequency. But what this forces, you do not get a higher spectral efficiency because you see those sideband distortions or ACPR or the sidebands coming up. So in order to get good linearity, you need to back off the PA. Now, once you back off the PA, you can see your efficiency drops, right? But you will get much higher ACPR specification, much better ACPR or ACLR specification. So these two are conflicting requirement. So how do we get best of both worlds? To operate PA with high PAE as well as have low signal distortion. And that's what we do with digital pre-distortion. So there are 2 approaches to solve this issue. One is to do PA linearization, which will allow us to drive the PA closer to saturation with a much lower level of distortion. And also the signal, which has a very high PAPR, you could do bit of signal preconditioning so that you can reduce the signal peaks without causing any significant distortion to signal or the input signal itself. And that's called CFR, crest factor reduction. And then you linearize the PA. So sometimes you only use DPD, or sometimes you use combination of CFR and DPD. So that's the solution. In my demo, I'm only going to show the DPD, not the CFR, because largely that's signal processing engineer who will end up doing that. So let's pictorially understand what problem we are trying to solve. Well, when we are driving our PA with the desired input power, our PA has certain compression characteristics, and that's what's causing the distortion, right? So what we can do by applying DPD technique is instead of having an input, kind of signature, once we know the nonlinearity curve of the PA, we can create an inverse of that and we can pre-distort the waveform which is going into PA so that these two things can cancel out each other as much as they can. And again, look at curve. There is always a sweet spot of DPD being employed at the right input power. If you feed lesser power or more power, you do not get a desired benefit by using DPD. But eventually, once you pre-distort the signal, feed it to PA, what you end up getting here is a linearized output because these distortion parts are canceling each other. So this way, your PA sees a bit of gain expansion, and then you can get a linearized performance with a lower out of band distortion. So that's in a nutshell how DPD approach works. So now let's see how can we utilize these DPDs inside ADS and linearize our PA to figure out what will it really take to linearize our PA. Now again, if you visit Keysight Knowledge Center, we do have a few DPD examples or templates which you can utilize. So here under DPD, so we have the same VTB. And again, I already told you where to get it VTB from. So under simulation VTB, you have this VTB template. Instead of using a regular 5G, I have used this DPT ET, which also has the capability to do envelope tracking in case you are doing an envelope tracking based PA. And here is your DPD with ET, or you could simply run a regular DPD, or you can have a shaping table based DPD, or to extract the shaping table out of your envelope tracking. So in my case, I have simply used a normal DPD because I'm not employing any envelope tracking. Now this DPD setup again is very similar. You can choose what kind of standard you are working with. Now, if you have your own unique INQ waveform for which you need to linearize your PA, you can do that as well. Now, depending upon what setting you are going to use here, like in my case, I have used 5GNR downlink, you can do respective block settings. So you can see here, name says IQ segment. So if you choose the signal type to be IQ, you need to be careful and set up these parameters properly. If you choose LTE, then you need to select LTE parameters. And if you use WLAN, you can set up WLAN. Or in my case, I have selected it to be NR. And the bandwidth is 100 megahertz. Numerology I have selected as 30 kilohertz, and the modulation I'm going full blown 256 QAM, which is the much denser modulation standard, and that's where the EVM spec is the lowest because obviously the samples per symbol is quite high, or samples per bit is quite high. Right. If you want to employ CFR algorithms inside this DPT network or VTB, you could enable that. But in my case, I have set it to no. And again, there are different DPD model types for you to choose, the model identification algorithms for you to choose. You can set up your desired DPD characteristics. But again, you can give it a little more time. And here the setup is very similar what we just did. And here I just connected VCVS, although it's not required right now, but in case you want to play with some of the input impedance to this amplifier, or you want to do a bit of sweep of input impedance looking at various sources, you can do that. But in this case, this is all 50-50 ohm, so it's actually transparent. Now, this VTB, when you run, you can select the mode of VTB. So first step in DPD, as we talked about in the slide, is to compress this amplifier and get that characteristics so that you can create inverse characteristics of this DPD. So that's the step number one. And step number 2, we are going to apply that pre-distortion waveform or pre-distorted waveform as an input to look at output results. So it's a two-step process. So in DPD VTB here, you have an operation and you can define 0 or 1. 0 means it is going to compute the nonlinear characteristics of this PA and then construct a DPD coefficients. And when you set it to 1, it will apply those coefficients in the waveform which comes out of this DPD. So in our case, we are simply setting up a parameter sweep with a variable operation. It will start 0, then it will go to 1 in a step of 1. So operation 0 means it will do DPD extraction, and 1 it will really apply the DPD. Rest of the input power is all set as per our previous extraction. When we run the simulation, it will launch a multi-minutes long simulation, because remember, we are doing a full-blown symbol based EVM kind of technique to apply this DPD to compute the ACLR along with EPM. So let me show you the final results which we obtained. So here in this plot here, let's look at this spectrum. So the red is input spectrum. The blue is what comes out of PA, and the magenta or the pink here is after we apply DPD. You can see how much ACLR has gone down. And the spectrum here is actually showing you only the without DPD and with DPD. And you can see almost you gain 20 dB kind of linearized output. So you enhance the ACLR by 20 dB. And again, the rest of the parameter here, if you look at the original signal had an ideal kind of ACLR. After the PA output, our like 33 dBm, and after we apply DPD, it gets improved to around 51 dBm. So which is an excellent 51 dB. And the 5G spec says you should be better than 45 dB, so kind of meeting the spec. If you look at output after applying DPD, we are able to obtain the required amount of output power, which is excellent. NMSE is a quick figure of merit to tell you how well we were able to create the inverse of the PA. Lower this number in is better for us. Now, in terms of EVM, I have two ways of looking at EVM. You can look at dB or you can look at percentage. So let's say in percentage. So ideal signal had a 29 milli% EVM. At the output of the PA for 256 QAM, it was around 5.3%. And after we apply our DPD and linearize the amplifier, you can see drastic reduction in EVM, which is close to 0.5%, which is much lower than what was there in the standard. So even if we leave a few things for fabrication tolerances or power supply tolerances, a little bit of imperfection, still you have a plenty of good margin built in to your design. Isn't that excellent? So you have margin built for yourself in ACPR as well as EVM, almost guaranteeing that you will have the good response after you fabricate and test this power amplifier. And here are some characteristics of DPD for you to see how well your amplifier characteristics are replicated by the algorithm you selected. Well, that was all about this tutorial. So let's go back to our agenda where we all started with. So we talked about in part 3 the 3 ways you could do the modulated signal analysis for your PAs or transmitter. We looked at VTB, CTS, as well as FCE based modeling. And then we talked about DPD, and I gave you a quick introduction, like a crash course on introduction to DPD. And then I tried to communicate to you how can you do DPD based simulation for your own designs. And in this case, we used 10 watt gallium nitride PA, which we created in this 3-part tutorial series. So hope you like the content presented in this video, and that gave you plenty of information to take back and apply on your circuits which you are designing. And you will have a much smoother learning process when you do this kind of analysis with your own designs in your copy of ADS. Thanks a lot for watching. And again, don't forget to like the video and share it with your friends and colleagues and put in any valuable comments in the comment section below this video. Thanks a lot, my friends, for taking out time and watching this tutorial. Wish you all the best with your design work.